Okay, welcome to our next compound object. Last time we did a ring of charge. Now we're doing a surface of charge, and I forgot to write with uniform charge density. Now this is a two-dimensional object. So when you have a two-dimensional object, you're going to end up with studying charge density as sigma, right? So it's not linear, it's surface. And in other words, when you find out how much charge is on here per unit space, you choose a bit of area to study. So you'll be using the idea of how much charge is there per unit area. Okay, so there's two things we have to pay close attention to. One thing is that if it's uniform charge density, then if you look at the whole area and you do total charge Q over total area pi r squared, that's equal to sigma. But at the same time, if you just pick, let's say, this little gray ring here, just this little gray ring, right? The area of that ring, or excuse me, the total charge of that ring divided by the area of that ring is also sigma. So sigma is a measure of how many, positive charges you'll find in any unit area. So sigma never changes no matter where you peek. Zoom in, zoom out, doesn't matter. Okay, so let's talk about a piece of area like that ring I just drew. So how do you visualize that? Well, if you kind of cut it, so I'm going to draw a pair of green scissors here. So if you draw a pair of green scissors, that's a horrible drawing. Okay, so you draw these little scissors and you snip it open, right? And you lay it out straight. It could be sort of visualized as a long strip that's sort of rectangular. So how long is that strip? Well, that strip originally was wrapped around in a circular fashion. So the length of that strip is whatever the distance is around this circle, which we're going to call 2 pi r. I don't want to use capital R because I don't think it's as big as the whole disk, but it's just this ring, you see. And if you look closely, there's an r here, which is the distance from the point beneath P to the gray ring I'm talking about, which I've colored red. Okay, so that would be the length of that rectangle, and then the thickness of that rectangle, the width of that rectangle, would be actually a small change in radius. So you can see here, it's real hard to see, but right there I labeled dr, and that little charge element, that little charged ring, has a thickness dr because it goes from r equals r, which is the inner radius, to r equals r plus a little. So it's a little bit longer when you go from the inside of the track to the outside of the track. And runners know that, right? When you're running, right? If you're on the inside of the track, it's a little bit smaller. Well, that tiny discrepancy there, I'll draw it in green, that tiny discrepancy right there is dr, we call it. And dr meaning it's so tiny. Like, if I wanted it to be like a little tiny, I would put delta r, but I made it really, 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 really tiny, dr. Okay? So what is the area of that strip? If you wanted to write down the area of the strip, you would say dA, because it's not the whole area, it's just a slice of area. And you would just do length times width, 2 pi r dr. Okay? So we'll come back to that idea a little later. So that's the first thing we need to notice. So whether we think of this as total charge over total area, or a small contribution of charge over a small contribution of area, they are both sigma. So this is a very important principle. Very, very important. Okay? Total charge is capital Q, total area is pi r squared. A small amount of charge is called dq, small area of strip was 2 pi r dr. And the ratio of charge per unit area is both sigma. Okay, so we'll get to that a little bit later. The other thing we need to pay attention to is the symmetry. So when you have a charged ring like this, we already said in the last problem that the vectors, the field vectors, can be broken down into components that are like right and up and left and up. And I didn't draw all the field vectors, but I drew two of them, and these are on opposite sides of the same circle, and they both contribute equal amounts of horizontal and vertical force. The difference is the horizontal forces, which they're probably better to call them radial because they don't have to be pointing left and right. They could be pointing forward and backward. Anything that goes from the blue ring to the point that I've just labeled as a star, any thing that goes into that direction we call radially inward. And those all cancel each other out because they're all pointing against each other. There's always one that points against the other. But if you look at the y component, or I shouldn't say y, because technically this is labeled z. If you look at the z component, the upwards component, you'll notice that those are constructive. They add together. You see, they add together. Okay, so the upwards field is all that matters. And now, I'm assuming, when I say upward field, I'm assuming that these blue arrows I drew are pointing away from the disk. In other words, I'm assuming a positively charged disk right now. Whatever we learned from this problem, we can easily apply to a negatively charged disk using common sense. Okay. All right, so there's a comment here that says, due to the azimuthal symmetry, only the z component is uncancelled. What I was just mentioning is that anything pointing straight up, any field vectors that point straight up are constructing. Anything that's pointing radially is going to destroy. So we have constructive and destructive. All right, now, what can we take from that? Well, looking at this triangle right here, that's just a spatial geometric triangle, right? And I'm going to draw it over here. When you draw the field vectors pointing at point P, we don't know if those are shorter than the black vector here or longer. That kind of depends on how charged this disk is. So the little red arrow is like the field vector. The black arrow is a position vector. Okay? Now, if it's a super low charge on the disk, then this little red arrow might be very short. But if it's a very heavily charged disk, then it will be a very long arrow, perhaps even longer than the black, if that makes sense. Okay? But regardless of magnitude, if we just kind of draw a vector in here that's E, it's just a small amount of E, say DE. And all of the DEs going around this disk, so if you draw another piece here, another piece here, and another piece here, all the DEs collectively form a small amount of field. So even though it's a whole ring, it's just a super thin ring, and it only contributes a little bit of field to the total point up here. So up here at P, we experience a field from the whole disk, but also from the gray ring below it. Okay, so we're going to need a cosine theta, and the reason is, regardless of which triangle you're drawing, whether it's a DE and legs DE cos, DE sine, these two triangles are similar. Whether you draw the small red one or the larger blue one or whatever, it doesn't matter. It's the same theta, so they're similar triangles anyway. And so we only care about the vertical component. We're going to look at DE cos theta throughout the problem. And if we're going to sum them up, we're going to integrate. So we're going to do DE cos theta under an integral. Okay, so this is going to give us, and we usually put the DE last, right? Or the differential is always last. Okay, now what is DE? Well, DE is the small amount of field charge from one ring. So we actually have that from earlier, but let's not focus on that. Let's just focus on the fact that it's always K times charge over distance squared. So the charge is dq, meaning a small amount of charge on this ring. It's not really the full Q, right? It's just a part of Q. So these are all positive, 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 but this whole positively charged ring is charged dq, not Q. Q is the whole thing, and dq is like the part of it. And then we have divided by the distance from the ring to the point. So how far is this ring from the point? Well, it doesn't matter where you are at on the ring. You're always row units away from the point at the top. So this is going to be a rho squared. It always goes kq over rho squared, but it's a dq. All right, so now I'm going to insert that expression in right here, right? So it's going to go like this, k cos theta, integral cos theta, and then I have, for dE, I have k dq over rho squared, or if you don't mind, I'm going to put the dq separate. I always try to keep the differential separate. Okay, we're getting somewhere. You might ask, well, what can I pull out of my integral? Well, we'll talk about that a little bit later. Okay, now, we said earlier that dq over 2 pi r dr is the same as total charge over total area pi r squared, right? This is going to give us a nice replacement for dq. So this is cos theta k over rho squared, and dq is going to be replaced with this now. dq will be replaced with 2 pi r dr total q over pi r squared. Oh, and that's a capital R squared on the bottom, and a lowercase r dr on top. Okay, so this is going to look like 2 pi r q, and then I'm going to put I'll put the dq outside completely. I like to do that. dq, and then we also have, or I meant to say dr, I mean. So yeah, 2 pi r q dr, and then all over pi capital R squared. And then some things start to cancel, and lots of things can be pulled outside. So what I got when I simplified it all, I'll show you. I know I'm kind of erasing a lot. That's just because I don't have as much space as I think you do. Oh, and I think there's a couple blanks to fill in down here too. I'll help you fill in these blanks here. So since sigma is dq over dA, we can write dq is sigma dA. I forgot I had written this. That's a lowercase q. Sorry about that. That should be a lowercase q. dq equals sigma dA. The differential element, area element was 2 pi r dr. The minimum and maximum values of r are going to be 0 and capital R. Okay, and okay, so going back to what we had written, we had originally kind of stopped, and I pulled some things out. I canceled that pi, and I pulled some things out. I can pull out the 2. I can pull out the k. I can pull out the capital Q. And I can pull out the capital R squared, because that's just a property of the disk. But left inside is an r, a cos theta, a rho squared on the bottom, and a dr. So we're almost done, guys. Hang in there. You will notice that cos theta, remember we drew a triangle earlier where this was r, this was z, this is rho, and theta was there. Cos theta, just geometrically, is z over rho, right? So we can insert that right here. Okay, so now we get 2kq over capital R squared sigma. Integral symbol. And then we have rz over rho cubed dr. Now, little r does change. As you look at different disks, little r changes, but z doesn't change. Z, remember, point P was up here, so now I'm kind of drawing above everything, but z never changes. It doesn't matter where you are on the disk, right? It doesn't matter where you're on the disk. The vertical distance to point P is the same no matter where you are on the disk. So z can actually pop outside as well. So I have 2kqz over r squared. And then this has an integral. And then we have the z is gone. So now we just inside have r dr over rho cubed. Okay. Now, I should have mentioned cylindrical coordinates here, not spherical coordinates. If you're working with these cylindrical type situations, you can see that the Pythagorean theorem, just from looking up here at this triangle, the Pythagorean theorem would go something like rho squared is equal to r squared plus z squared. So I've written that here. I've solved for rho, and this gives us our integral again, but it's a little more complicated now. Now it's got the 2kqz over capital R squared outside, but inside we have RDR over square root of, and then we have z squared plus r squared square root, cube root, the cube of the square root. Whew, okay, so that's row cube there on the bottom. I'll rewrite it one more time, it's a little messy. Sorry, there's a lot of students outside my room, just being real noisy today. Apologize for the distractions. Okay, I politely asked them to quiet it down a bit. So we have, I was just going to rewrite it one more time so you can read it. It's, that's a 2, not a cube. That's 2k capital Q over r squared integral RDR over, and then rho cubed. So rho is z squared plus r squared square root. So it's half power, but we're cubing, so it's 3 half power. Okay, it's been a while since we've done a u substitution, but we're going to do a u substitution integral right now. It's been a long time. I'll change this to cylindrical. Sorry about that. All right. Going down, let me clear this stuff out. It's kind of my solution. Okay. I'd like to let u be the entire inside of the denominator here. So let's let all of that represent u. And then the du would be the derivative of that. So if you take the derivative, so I'll show the non-calci students how I'm doing this. So I'm going to pretend u is r squared plus z squared. So when I take the derivative du dz, I end up getting, I treat r squared like a, I meant to do du dr. I'm going to find the derivative as if r is like my x. So this is going to give me 2r, but the z squared is going to just vanish. Because, for 2 reasons, z never changes in this problem, we said, and also I'm not treating z as dependent on r. I'm just pretending like r is my x, and I don't see any x's here. So z squared, as far as I'm concerned, is like a constant for a couple reasons, and I'm just going to leave that as derivative 0. Okay. So then moving the dr to the right side would look like this. So du is 2r dr. That's just basic u sub for my Calc BC students, but if you haven't seen that before, that might be kind of complicated. Okay, if you look at your integral, you will see I've highlighted in the integral in green a z squared plus r squared. That we will now call u. I'll write that in green also. That's going to be called u. And if you look on the numerator, you will see up there is a 2 and an RDR. That's going to be called du. Okay, so when I rewrite this integral, so that top part's going to be called, sorry, I was going to use green for that. This 2r dr is going to be called du. Okay, so this allows me to write my integral a little simpler. I guess I'm bringing that 2 kind of back in. Anyway, this gives me du as a numerator, and then a very simple denominator, just u to the 3 halves. Just u to the 3 halves. And that integral is not hard to solve. Okay? So now let's rewrite it. So we have kq over r squared, and we're going to rewrite the u to the minus 3 halves as u, I'm sorry, the 1 over u to the 3 halves as 1, as a u to the minus 3 halves. Remember, to find an integral, we do an antiderivative. So you're going to ask, how could there be a u to the 3 halves? Well, you're going to find the antiderivative. So you just basically add a power, which gives you u to the negative 1 half, because it added 1 to the power. And then you put the reciprocal of that new power out in front. So what's the reciprocal of negative half? Negative 2. Okay, so you might say, what did you just do? That's like magic. Well, this is how we find an antiderivative. We basically add 1 to the power, and then we take the new power, which is negative half, and we reciprocal it and put it in front. Okay? And this function right here, if you take the derivative, it takes you right back to u to the negative 3 halves. Okay? So that's called doing an antiderivative. I've been a little sloppy with boundaries. The original problem was written in terms of r, and we just changed it to u's, So we better change it back. So right now it looks like this, negative 2kq over r squared, and then there's a u to the half down here. But all of this was integrated between little r equals 0 and little r equals big R. Those were our boundaries of integration from earlier. Right? So we would treat those as the a and the b from the fundamental theorem of calculus. So we have r equals 0, r equals big R, and then you would do r equals 0, r equals big R. So I got a little sloppy with not writing the limits of integration on there. And now we are going to change u back to what it meant before. So u meant r squared plus z squared. So Mr. Storr is just going to erase his u to the half. He's going to put back in the r squared plus z squared to the half. And now when you plug in the capital R and the 0, you get something like this. Negative 2kq over capital R squared times, then you plug in the capital R, so it's 1 over capital R squared plus z squared squared, I'm sorry, to the half, and then minus, and then 1 over 0 squared plus z squared to the half. So this just becomes, basically just becomes z, because capital R is, little r is 0. Oh, and it occurs to me when I did a little bit of copying, like I was copying things down the page, I did drop a z that was outside the whole time. So there was a z that was outside the whole time. And I think what I did to kind of clean this up a little bit is I distributed a z back inside, and I think I distributed that negative also. So it kind of flip-flopped the two fractions on the inside, and it made the second one a 1. So like this would be a 1 if I redistributed that z. Okay, so here's what I got. Right at the top of the page, I got 2kq over r squared. The negative is going to be distributed in, as is the z. So let me show you what I'm distributing. I'm distributing this negative and this z. Okay, so on the inside then, the fractions reverse, and the 1 over z fraction ends up first. But you're multiplying by negatives. Oh no, I'm sorry, I didn't flip them. Hold on. Oh yeah, the positive fraction becomes, whoops, I just erased it. That was a 1 over z. Haha. Sorry, this was a 1 over z, and I just accidentally pressed erase. Okay, so that fraction flips over to the first spot, but you're multiplying it by z also. So this is just a 1. And then the other one's going to be the minus fraction. So anyway, you probably work faster than I can talk on stuff like that. And I changed the radical back to, or half power back to a radical. So why did I write it like this? Well, I kind of liked the kq over r squared outside. Kq over r squared just reminds me it's a field. This is the net field due to a charged disk. Okay, and what's nice is I can see, oh, there's a kq over r squared. That's a field. Everything on the inside is unitless. So I'll show you real quick. Like this is obviously no units. This is meters. This is meters squared plus meters squared square root, which is meters, and meters per meters is 1. So in other words, there's no units on the inside. All the units are collected outside, which makes it a little easier to understand. The 2, I don't really like the 2 where it's sitting, but I guess he's better there than he is inside. But you can definitely tell this is a field because of the kq over r squared field. So it's Newton per Coulomb. Man, that's complex, right? Well, believe it or not, had I picked a point that was not directly above the center of the disk, if my point P had not been at the very center of the disk, this would have ruined everything. Okay, unless we were so close to the disk, vertically speaking. So let me take that answer I just had, and we're going to do a couple things with it. So let's talk about some extreme cases here. Oops. Okay. Oh, and just a quick comment about my integration methods. When I work on paper, I work a little smoother. I sometimes pull things out early, regret it, bring them back in. You know, I don't know if there's one faster way to do it, you know. But as you practice this kind of thing, you will find yourself being more adept at knowing what to pull out and when you want to pull it out. If you want to, you can just leave everything on the inside and then in the end pull everything out that belongs outside. You don't want too much inside your integrals because then it just feels too difficult. But you also may have to have things on the inside to help you with the integral. So never pull something out if it's changing, right? So like in this problem, z never changed, and neither did capital Q, and neither did capital R, and neither does K, of course, that's Coulomb's constant. But like things like little r, things like little rho, those change as you move around on the disk. So you leave those inside and try to get it all down to one variable like I did. And the way I did is not the only way to do it. Anyway, here's the summary answer right here. And I wanted to talk about what we could do with this charged coin. Okay? So I was just saying a second ago that with this charged disk, if you try to study points that are not directly on the axis of symmetry, the field gets very complicated, folks. If you thought what we just did was hard, imagine if you tried to do it off-center. Okay, that would be much harder. Okay, so what we usually try to do when we finish an example like this is sort of ask, well, when is it valid? Well, imagine if you really shrunk z down and you were just barely above the plane. Okay? Now, when you're looking down upon a coin, but you're really, really close to the coin looks bigger than it does when you're standing further away, right? So if you're way up high looking down on the coin, you're like, oh, tiny coin. But if you're right up next to the coin looking down, then you say, oh, huge coin, right? It's a perspective thing. All right, so if we get z closer to 0, if we say, hey, let's get in real close, up close and personal with the surface, what we realize is that z basically is getting closer to 0. Okay? All right, so you're going to end up doing, actually, do I want to, I don't want to think of it as z is getting closer to 0. Mr. Shaw doesn't want to think that. Don't think of it so much as z is closer to 0, but think that capital R is much, much bigger than z is. Think of the disk is much bigger than the distance we are above it. So it's kind of the same idea, but think of R as much bigger than z. Okay? So what happens is, in this problem, you're basically letting you're doing the limit, but it doesn't really affect anything except this inside right-hand term. So we're going to do limit as, I was saying R is much, much bigger than Z. Let's think of it as let's think of it as Z over R is approaching 0. So if Z over R is just a teensy-weensy fraction, meaning R is much bigger than Z, you can kind of apply that idea and play around with this limit a bit. So what happens is you have to kind of divide top and bottom by R squared, but you end up just losing this second term altogether. So this whole part's going to go to 0, and then you just end up with 2kq over R squared. So what's really interesting about this is it almost looks like just the old definition of E, right? E is just kq over R squared. Notice that with this coefficient out front, 2, that's not going to make it hard to remember. Okay, now what is this though? Is when you get it up close and personal with a disk, in other words, if you're, I think the way the book says is they're just going to, I said z over r goes to 0. They're just saying, look, let's let r go to infinity, but don't change z. That's another way of saying it. Same thing I said, z over r goes to infinity. I mean, z over r goes to 0. Basically, if the disk is super, super, super big compared to your height, then you actually get this. So this would actually be more of an infinite plane of charge. Because we got up so close to it, right? And the r kept getting bigger and bigger, and the z, we just got, we treat it as getting close. Or even if you just stay, just stay z, and then you just let r get really big, the coin gets super big, and then it feels like a large plane instead of a coin. Okay, so sometimes we use like the little coin, and then we expand it to get the truth about an infinite plane. All right. We will use this again later when we are dealing with sheets of metal and stuff that are charged, or even insulated sheets that are charged, insulating material sheets that are charged. Remember, insulators can hold charge. They just can't, the charges can't move around very well. All right, so that was pretty tedious, right? Half hour to do one problem. Okay, the last part of this video is just some comments. Later we're going to learn Gauss's law. It's actually coming up in the next chapter. If you look ahead, that's the name of our next study. And after we learn Gauss's law, we are going to be much more proficient in finding electric field. And we're going to be able to do it at points near various objects, whether it's a dipole, a ring of charge, or a disk of charge. We will have better and faster ways to do that later. I want to refer you to page 642 in our book. This is just excellence right here. So, as you can see, this is very tedious work and very challenging work. So I wanted to show you kind of what our book says about it. I'm just going to read it to you. I think having this little tiny bit of the book on YouTube is not really a violation of copyright law. I give, of course, full credit to the authors, Halliday, Resnick, and Walker. This is the 10th edition of the Halliday, Resnick, and Walker textbook titled Fundamentals of Physics. And it's published by Wiley. Okay, it says here's a generic guide for finding the electrical field E produced at a point P by a line of uniform charge, either circular or straight. The general strategy is just to pick an element dq of the charge, find dE due to that element, and then integrate dE over the entire line of charge. All right? So that's what we did. And it talks you through the case where if your strip of charge is a ring, like this, it says what to do if the strip of charge is a straight line. Okay. And then it says relate the charge dq. So relate the charge dq to the length of the element. So you want to have something like dq is lambda ds or dq is lambda dx if you're going a straight line. S is like an arc length. ds is like an arc length. And then you have your charges on it, like this. So lambda then would be how much charge you have, dq, divided by how much distance you have, ds. If it's in a straight line, we don't usually use s. Well, we can, but you might just think of it as like along the x-axis. So it's all kind of more straight and linear, and you just use like a dx there, okay? All right, next it says to express the E field, the dE produced at your point by dq. So you're going to go back to replace the q that's in your equation with either lambda ds or lambda dx. Don't forget that E fields point directly away from dq if it's a positive charge, but towards dq if it's a negative charge. So I did my disk positively charged, obviously. I never used a negative there. Step 4 says always look for any symmetry in the situation. If P happens to be on axis of symmetry of the charge distribution, resolve that E field into produced by components that are perpendicular and parallel to the axis of symmetry. Consider a second element dq prime that is located symmetrically to dq about the line of symmetry. And at point P, draw the vector dE that this symmetrical element produces and resolve it into its components. One of the components is a canceling component, the other is an adding component. So I had already mentioned all this, but this is such good reminders. Okay, if you're dealing with other uniform charge distributions, like a full ring, like if you're going to turn this into a full ring, not just a little strip, or just a circular arc, which is part of a ring, so like a ring is like this, circular arc is like that, or a straight line, you're just going to have to integrate to collect all your little dE's together. And that can be the hard part, but I found that most of the final integral step, like when you're finally doing the antiderivative, the hardest one we did was a u-sub. I mean, at least it wasn't like partial fractions or something, right? And hopefully that we don't run into any of that ugly stuff, integration stuff. Just add a power and put the reciprocal up front. Okay, next is how to deal with a straight line. If you're dealing with a straight line, it tells you how to do that. I didn't actually do a straight line. That'd be a good one for you to try. There's an example right here. It kind of shows you what you might want to think about. And the other thing is, don't forget when you're doing your integration, don't forget about limits. Limits. Okay? All right. So next time we will talk, you can see I've got my notes here. Next time we will talk about 22.6, which is electric charges in an electrical field, which of course means there will be a force on that charge. So we'll go back to forces, basically.